Good afternoon and welcome to Catalan Cymru revision sessions. And now this session will focus on AS chemistry and specifically today the VSE PR theory. And this session will be presented by Mr. Peter Black from Penglai School. Now the session will last around 45 minutes where the teacher will go through the relevant subject content with you. But as always, if you have any questions, please use the Q&A section at the top of your screen and I will do my best to answer your questions during the session itself. Now the session will obviously be recorded with the recording and any relevant resources then uploaded to the e-sgol website in the Catalan Cymru area.
Hello, right, okay, so as I say, we've been told we're going to be looking at VSEPR, which is a model for predicting the shapes and bond angles within a molecule. So it's, obviously it's something that's examined in year 12, but also throughout year 13, you're going to be kind of using VSEPR because shapes and molecules are very, very important. So let's get started then. So just a quick acknowledgement to Knock Hardy Publishing. Got lots of slides from here, some of my own as well. Right, so VSEPR, let's get into, let's get started. So, there are some things that you should know, hopefully by today's lesson. We're just going to be kind of recapping them. So we've got our the electron pair repulsion theory, we've got the regular shapes we see and bond angles and all sorts of stuff and the effect of double bonds. So those are like the contents what we're going over today. So hopefully you know these words, a covalent bond, what a covalent bond is. That was my session last week or the week before. Yeah, last week. You'll know what a lone pair is, and you know that like charges repel. So electrons are going to be repelling each other, and that's really, really important to obviously the shape of a molecule. So we've got a molecule here. Let's say, for example, we've got a central atom, and what we're trying to say here is, what shape would the bonds adopt if we had 3 bonds around this atom? Well, what they would do is they'd try and repel each other. And if repulsions are equal, we wouldn't expect to see this kind of shape in our molecule here because, obviously the bond angles here are much shorter than the bond angle here. So what we actually find is that if the repulsions are equal, and they're not always equal, as you probably know, then the bonds will be, bond angles will be the same. So that's just that little slide there for you. Okay, so moving on. So, as I say, if you've got equal repulsions, you're going to have what we call a regular shape. And if you don't have equal repulsions because of lone pairs, you'll have a distorted shape. And so I'm going to go through the regular shapes first, and then we'll look at the distorted shapes after that. Okay, so these are our regular shapes, and you need to know the names of these shapes, and you also need to know their bond angles that are associated with them. And you also need to know examples of them, or certainly you'll be able to identify them. All right, so let's get started looking at these regular shapes then. These are regular shapes, and all the shapes you do in VSEPR are based on these. So they're either going to be this shape or they'll be based on this shape. And you can actually see this is an image that I've got here, but I've blanked off this section here, and you'll see what that section corresponds to in a moment. And down here it says steric number, but what that means is basically how many electron pairs do you have around your central atom. And you got your linear, trig-planar, tetrahedral. You see these are a bit more unusual, and they kind of more important in year 13 chemistry than it is year 12, although you could be asked to draw them. In year 12, your trigonal, bipyramidal, these are your octahedral. You see your octahedral has got 6 electron pairs. Okay, so let's move on. So we'll look at some bonding diagrams then, and just apply this principle of the electrons repelling each other. And we'll start off with something like beryllium chloride. Okay, and now beryllium chloride, you can see here, is covalent in nature, BCl2, and you can see that in order to become stable, hopefully you're familiar with this diagram, a dot and cross diagram. You see here the views green and red to represent the electrons, but the key thing we do now, if we're wanting to look at the shape of this molecule, is we'd look at the central atom. All right, so we're not interested in what's going on either side of the central atom. That's got absolutely nothing to do with this. You can have many electron pairs you like there. It's the central atom. And if we look, we can see here we have got 2 electron pairs. So on that basis, once you've got your diagram, you can then look at your shape. So if we go, and hopefully you can see there that the electron pairs, we have 2, and none of those electron pairs are what we call lone pairs. So lone pairs, remember, are electrons that aren't involved in bonding. All right. So this doesn't have any lone pairs on the beryllium, just 2 bond pairs. And we go to our shapes now. It's like quite a useful image, this. We can see with 2 electron pairs, and they're both electron bond pairs. We can go for our basic shape, which is linear, and we have this bond angle of 180 degrees. So this is called the linear shape. Okay, so that's how you might draw it in the exam. So what about if we put another atom into our molecule? Well, there's our linear shape. We've got the 2 electron pairs, and we can see now we're trying to introduce another electron pair. So we're bonding with another atom now. So we're bringing a 3rd atom, and now you can see our bond angle has changed. As this electron pair comes in, it's repelling those electron pairs or bond pairs that are already there, and it gives us this shape, and hopefully you know that shape. So we'll have a look now at the next slide. So an example of this kind of shape, or molecule that adopts this shape, is aluminium chloride, and hopefully you can you know, predict what the bonding would be. I always, you know, students get a little bit sort of surprised when they think of aluminium bonding this way. This is obviously a covalent molecule, a simple molecule, and students always kind of have that kind of problem with this, because they think, well, aluminium's a metal and chlorine's a non-metal, so surely it should be ionic. But we know now, we've got a more refined understanding of bonding, and hopefully you know why it's covalent, and it's to do with the, you know, well, there's a couple of things: the difference in electronegativity, but also it's the, you know, if you're pulling 3 electrons off aluminium, that's going to be quite difficult to do. So it adopts this covalent structure, and this is, as I say, 3 electron pairs. So just bear me a second. So you can see we get our shape there. We have our 3 electron pairs, and what's important about these electron pairs is that they are all bond pairs. There's no lone pairs again on the aluminium. So we go to our basic shapes, we look for our number of electron pairs. So we've got 3 electron pairs, none of them are lone pairs, so we go for our trigonal planar shape and our bond angle of 120 degrees. So now this gets interesting. So far we've been working in a 2-dimensional aspect. We're now going to go into molecules that have a 3-dimensional aspect. So the other molecules, you know, you could draw them flat, and that's what they would look like. But this is where we introduce a 4th pair of electrons, and you can see what they do now is they squash these bonds in the trigonal planar shape downwards, and this brings us into a 3-dimensional molecule. This isn't flat. This is you know, it's got a 3-dimensional shape, and this is a very, very important molecule. And the reason for that, you know, I think if you think about bonding and why atoms bond, you know, it's to get that full outer shell, and we typically think of our full outer shell being 8 electrons, and so therefore we'd be thinking of 4 electron pairs. So this is a very, very common shape that a lot of molecules are based on, obviously not all. So let's look at some examples of where we might see this molecule. So methane is a really obvious one. Okay, so if we look at the bonding methane, hopefully you'll be familiar with this molecule here, this bonding diagram. You can see if we look on the central carbon atom, we have now 4 electron pairs, which is this tetrahedral shape. And there's our bond angle. Now, you have to be able to draw tetrahedral molecules, and well, my students are quite bad at drawing them quite often. Not all of them, but it does take a little bit of practice and a bit of confidence. Make sure you can draw it. The way I draw them is I always start with these bonds here. Okay, so what we would call the planar bonds, the ones that are in the same plane. And this shape here represents the hydrogen coming out of that plane towards us, and this one going into the plane. And the bond angles here are all 109.5. And we call this shape tetrahedral. Okay, so you can see the shape there, you can see that three-dimensional shape. So now we move on to something like phosphorus pentafluoride. And yeah, you're going to have to know a bit more of your chemistry when you come on to octet here. I think that's year 13 chemistry. But you know, you don't need to worry about the fact it's got more than 8 electrons inside its shell. All you need to worry about is how many electron pairs does it have. And we can see here that it has 5 electron pairs. Okay, so this gives us this shape here. It's trigonal bipyramidal. And again, you know, make sure you can draw the molecule. And it's called trigonal because you have this trigonal planar shape for 3 of the bonds. So that's your 120 degree. And then above and below that plane, so this is flat, above and below that, you've got these fluorines sticking out. And they're at 90 degrees to each other. So we actually have these 2 bond angles in the trigonal bipyramidal. And the reason it's called bipyramidal is because you can form a pyramid above for these points, and you can form a pyramid below for these points. So that's why we call it trigonal bipyramidal. Trigonal because of the trigonal plane there, bipyramidal because of the 2 pyramids we can form on top and below. So shape, we have 6 electron pairs, and again our shape there would be what we call octahedral. All right, so you can see here all the bond angles in this molecule are at 90 degrees. Again, you know, these are all regular shapes. All the ones we've looked at here are regular shapes because we don't have anything other than bond pair electrons. Regular shapes done. There's no more for you to worry about. That's a way of drawing it. If I was in the exam though, let me just go back on my previous slide. Second. That's what you would draw in the exam. So again, practice it. Again, you can see these are in the same plane, and then these are sticking above and below that plane. So let's look at the next molecule then. So if we move on now we can see that these molecules have our lone pairs in. Right, and this is where things get a little bit more tricky, perhaps. Or shouldn't get tricky, but you know, there's an extra layer to our learning. So how do we deal with this? Well, let's look at what we call our irregular shapes. These lone pairs are more repelling than bond pairs, and the reason they're more repelling than bond pairs is because the electrons are more densely packed. So if you think what a bond pair is, the electrons are being shared between the 2 nuclei, so they're being stretched out between those 2 nuclei. So they're more diffuse in terms of their charge, whereas a lone pair is a packet of negative charge, really kind of concentrated, and so it's more repelling than a bond pair would be. And it's worth knowing this order repulsion. So we say bond pair repulsion is greater than lone pair bond pair repulsion, which is greater than your lone pair repulsion. Okay, so for example, if you look here, I've got here what would be classed as a bond pair and bond pair repulsion. Here I've got a bond pair and a lone pair repulsion, and here we have the lone pair repulsion. And hopefully you understand that what happens is that the lone pairs, because they're so repelling, are going to push each other away as much as possible. And that will be at the sacrifice of our bond pairs. Our bond pairs are going to stop being pushed close together. So we'll look at ammonia, which is a compound of nitrogen and hydrogen, and I'm sure you're quite familiar with the dot and cross diagram. And what we're going to do now, this is where you need to just follow the rules of doing VSEPR. The first thing you do is you count your electron pairs, and you don't distinguish between bond pair and lone pair. You just literally count how many electron pairs you've got. So we've got 1, 2, 3, 4 electron pairs. And what we do now, if you just make a little note to ourselves, 4 electron pairs, but one of them is a lone pair. Now what we do is we go to our basic shapes and we look for the shape that would associate with 4 electron pairs. And that shape is our tetrahedral shape. So we know it's going to be based on this tetrahedral shape. But not all your repulsions are the same, because what we said about these bond pairs. So what we're going to do, first of all, I've got this molecule here, and you've got that shape, and you'll recognise that that's a bit like the shape for methane. And you can see that the lone pair are occupying where the carbon-hydrogen bond would have been. So your lone pairs are occupying that region space. So it is there, and it is repelling. Lots of people forget about this, and they'll start to think that it's perhaps trigonal pyramidal, because they can only see those 3 bonds. They think, oh, well, trigonal pyramidal. But this is like a ghost bond. I always think of it as a ghost bond. It's there, you just can't see it. Okay. So in terms of the shape then, if we were thinking of it being based on tetrahedral, we'd associate that bond angle of 109.5 between the bonds. But because our bond pair repulsions are greater, your bonds here, these nitrogen hydrogen bonds, are pushed in closer together. So you can see the lone pair there is pushing this bond down away from itself due to its great repulsion, and that squeezes these bonds in close together. And what we tend to say is for every lone pair, you tend to lose 2.5 degrees on your bond angles. Okay, so when we come to draw the shape, this is the shape we have. We call this is like the shape is called pyramidal, and hopefully you can imagine that if you connected up your atoms, you would have this pyramid shape. And we have this bond angle here of 107 degrees. This is our pyramidal shape. Very, very important shape to know. Okay, moving on. Oh, yeah, there's a couple of more pictures there of your pyramidal shape. Okay, so this is the shape, why we call it pyramidal. Again, make sure you can draw it. It's basically the tetrahedral shape without the bond. Let's look at water. So we have our water molecule here that we've got drawn out. And again, if we look at our electron pairs, we can see here we've got 1, 2, 3, 4. As I said to you earlier, that tetrahedral shape is probably the most important shape for you, because most of your molecules are going to be based on it. So if we now have a look at going back to our shapes earlier, hopefully you'll know that it's based on this tetrahedral shape again. So you can see our tetrahedral shape, but instead of there being bonds in these positions of the tetrahedral shape, we have our lone pairs. And you can see these lone pairs, they're going to try and push each other away as far apart as possible. So we're going to have the maximum bond angle here. And a consequence of that is that these are being pushed in together. So it's this order repulsion. The lone pairs are going to try and get as far away as possible. The bond pairs are going to be pushed away by the lone pairs into each other. And again, you can see our bond angle has reduced by another 2.5. So if we went to our original bond angle, we're at 109.5 for the methane. With the ammonia, with the one lone pair, got reduced to 107, and now with the subsequent lone pair, it's been reduced down to 104.5. And the shape here, well, on this PowerPoint it's described as angular, but on your syllabus you tend to describe it as bent. And the reason it's described like that is, if you think about what water would look like if we didn't have these lone pairs having an effect, it would be a linear molecule. But these lone pairs do have an effect. They are there and they are repelling. So it's called bent because you've bent out of that linear shape. Okay. Just a little one for you here, an interesting one. What's that then? Well, let's have a look. This is xenon tetrafluoride, and if you did your dot and cross diagram, you may not known that xenon can join it, but fluorine is, very nice. Just want to join it, so you can form this molecule. And what kind of shape would that form? Well, if you count your electron pairs, we have, let's see, 6 total in total. So we have 1, 2, 3, 4, 5, 6. And if we went back to our regular shape diagram that I showed you earlier, you'd know that you'd have your octahedral shape. And hopefully you can understand why we've got our lone pairs in these particular positions. And that's because they're trying to get as far away from each other. You obviously want to put a lone pair here because that would be at 90 degrees. So what they've done is they've taken completely opposite sides of the molecule. So the bond angle between your lone pairs be 180 degrees. Now, you won't get this shape. It's just I put it there as a little bit of an extra layer on your learning. Okay, we've got a shape square planar. So the trigonal square. Okay. So, what I'm going to show you is a very quick way of actually working out a shape of your molecule, because in all those pictures, well, in all those things we've been doing there, we've actually been having to draw the dot and cross diagram. Now that can get a little bit trickier, you know. So if it was methane or ammonia, we wouldn't have a problem with that. But sometimes, you know, the molecules they'll give you can be quite difficult. In fact, one of these is from a past paper. So this molecule here, ClF2-. So there's a nice little kind of table you can do. And obviously, you don't need to draw the table out in the exam, but it's kind of worth remembering how to do it. So I'm going to run through each of these with you, and then hopefully when you play the PowerPoint back, you'll be able to do it yourself. So what we do then, we've got our formula that we're predicting the shape of the molecule for. We've got NH3, ammonia, which is a fairly straightforward one. You could draw the dot and cross diagram. But what we do is we look at the valence or central atom. So our central atom here is going to be the nitrogen, and that's in group 5. So we know that's going to be 5. And then we've got the number of bonds. So there are 3 bonds to it. And I'm just going to click this off now so you can see. So what I've done then is I've got my valency, 5, and there are 3 bonds to that in that molecule. And what I do then is I look if the molecule's got a charge, and this molecule doesn't have a charge. And you see I put here a little thing about, you know, if you've got, well, that's sorry, I have to change that on my PowerPoint. It's a little bit wrong. Well, it's not wrong, it's just the brackets are in the wrong place. If you've got a positive charge, you take an electron away from it, as you would expect. And if you've got a negative charge, you're going to add an electron to your total of electrons. So because this doesn't have any charge, I've got 8 electrons on my central atom. What I do then is I look at how many bonds I've got. So I go back to this. I say, well, I've got 4 electron pairs. If I've got 8 electrons, that's 4 electron pairs. 3 of those bonds are bond pairs. So the 4th electron pair must be a lone pair. And that now, 3 bond pairs, lone pairs, I can go to my table, and I will do this with you in a moment, and predict the shape. Obviously, this is our pyramidal. So let's look at the ammonium. I'm just going to pause just very, very quickly, only enough for you to actually pause it if you're watching the video. I can have a cup of tea. Hopefully, once you've paused it, you'll be able to work out your number of bond pairs and lone pairs. It's a really quick way of doing it. So again, our valence is 5 with 4 bonds. You can see here, though, I'm going to take away an electron because of its positive charge. That gives me 8 electron pairs. I come back then, sorry, yeah, 8 electrons, which gives me 4 electron pairs. And now what I do is I just look at my bonds. I've got 4 bonds. I've got 4 electron pairs. They must all be bond pairs. Kind of look at your shapes of molecules or number of electron pairs. I'll pause again, just briefly, for you to do NH2-. So you can pause your video, and I'm going to click back on now. So you can see NH2. Again, we've got a valency of 5, number of bonds 2. I'm going to add an electron because of its negative charge. So 5 plus 2 is 7. Add on the electron gives me 8. That means 4 electron pairs, 2 bond pairs, 2 lone pairs. And finally, ClF2-. Again, just a little pause for you. And let's have a look. Okay, so chlorine is in group 7. There's 2 bonds, and we're going to add an electron because of the negative charge. So that gives me 10 electrons, 5 electron pairs. 2 of them must be bond, 3 of them must be lone. Okay, so it's just a nice little method for working out your number of electron pairs. And then what we can do, based on the number of electron pairs and bond pairs and so on, we can predict our shape. So let's just do that really quickly. I'm going to actually pause for you to just have a little think yourselves, and then I'll quickly run through it. Okay, so you can see the first 4 shapes are all going to be based on our tetrahedral. shape here. Oh, sorry, not tetrahedral shape. Okay, it's the 4 electron pairs. And then they're going to obviously have some issues with the number of lone pairs. So if you've got 1 lone pair, remember that's going to be there in that position. That will give you pyramidal shape, and your on a 7.5 bond angle. Here we've got 2 bond pairs and 2 lone pairs. So now we're going to have a lone pair here and a lone pair here. So it's still basically tetrahedral, but our bond angle now is much smaller at 105. And then this molecule here will obviously be based on kind of this trigonal bipyramidal shape, but we won't go into how that particularly looks because that's above year 12, probably above year 13. Okay, so now we're going to talk about double bonds because so far we've kind of ignored those. So if we talk about double bonds, you can see here, this is a really important diagram to be able to draw. It's carbon dioxide, so please make sure you practice drawing that. It's it is a GCSE kind of thing they ask you to do, but they can ask you to do it at A level as well. Now the important thing about your double bonds is they only count as 1 electron pair. Okay, so if you've got any electrons in a double bond, you only count them once. So if we look at carbon dioxide then, and we look at the electron pairs, hopefully you can see in terms of electron pairs, in terms of shape, there are only 2 electron pairs, and that gives us our linear shape, this bond angle of 180 degrees. Okay, now I might try and show you another one of those in a minute. Oh, here's a nice one. Okay, now this is way too complicated for you to worry about, but it does show you the principle again. You wouldn't be expected to draw that. However, if they drew that for you, why not? If they drew that for you, hopefully you can see each of these lines, I'm sure you are aware, represents a dot and a cross. All right, it's a covalent bond. Doesn't look like anything's dated there. So, if I was to count my electron pairs on this molecule, the sulfur's not got any lone pairs left over because it's used all its 6 electrons. 1, 2, 3, 4, 5, 6. Okay, so there's no lone pairs there. And in terms of the shape, we can see here we've got 1, 2, 3, 4. So in terms of your shape's tetrahedral. You've got 4 electron pairs. Okay, so even though it looks quite challenging, quite difficult, as long as you know what these bonds are, electron pairs, double bond, doesn't matter, it's 4 electron pairs. So there's your shape for that molecule. The sulfate ion, hopefully you recognise. Okay, so I thought, it's always good to practice, so you can draw your table up. Obviously I'm not going to do these now with you because hopefully that's kind of a skill that you can practice yourself in your own time. Remember, these videos are great because you can pause them. I've put that little table there for you to have a go. If I was in an exam, I would just literally sketch that very quickly at the, and on the back of the paper just to help me, or even on the question itself. Why not? So, yeah, use that method. It's really helpful. I'll put the answers there for you, so you know whether you're right or wrong, because that's always nice to know. And that's you kind of your VSEPR, the theory, and the theory is great. It's great that you can predict your shapes and molecules and blah blah blah. But the challenge is the exam, because the exams are how do you answer questions about VSEPR? Well, if you're drawing the molecule shape, that's fine, but the actual questions that they want a written answer to can be quite well. What do you say? So I've thrown in some past paper questions now for us to just think about this. So here's a question we've got, and you'll recognise actually that's the one I said was on a past paper, and it says, well, ClF2 plus and ClF2 minus are 2 other ions containing a chlorine atom. The student said that their shapes must be different. Is he correct? Justify your answer using VSEPR theory. Okay, what do they want us to say? What do they want us to do? So the first thing, when you're looking at answering a question, and I'm going to give you a bit of exam technique you probably know already, is the first thing is, well, how many marks is it worth? How many things do I need to say? So we've got to say 3 things here. And then it's kind of, well, what are those three things that we're going to have to say? Well, the three things you're going to have to talk about is, first of all, is he correct? Okay, and why? Well, if you look at the mark scheme, what the examiner is asking you to do in these kind of questions is to work out how many of those bond pairs and lone pairs are around that central atom. And like I say, you know, you can do that very, very quickly and very, very easily by looking at the using the table format that I kind of showed you earlier. And then how do you justify your answer? Well, you know, this is quite a common question that I've seen in past papers, and it's very simple. I mean, you could write an essay about why they're different shapes. All the examiner wants you to say is there's different number of electron pairs, there's different shapes. Okay, or if, let's say, the number of electron pairs were the same, you could say they have the same number of electron pairs, but one of them is a bond. In one molecule they're all bond pairs, and in the other molecule there's a lone pair. All right, so you just keep it very, very brief, very simple. You're just literally talking about what's different in terms of the number of bond pairs and also the types of bond pair. Okay. So I've got another question here, and this brings me on to something extra. Okay. Oh, hang on, no, it's a similar question to that one. It's the one coming after this. This is again, you know, using the principle of valence shell electron pair repulsion, statement explaining the shape of a molecule of H2S. So what I'm going to do again is just leave that brief pause, so you can pause it in the watching the video, and you can perhaps think about your answer here. And you know, hopefully drawing the shape's going to be okay. Explaining the shape, well, let's see what the examiner's looking for. So using my method here, you may not need to use that method. You know, it's only something that I'm going to suggest you use. I insist. There's my H2S, okay, and 2 bond pairs and 2 lone pairs would give me that bent shape. Okay, remember that's based on the tetrahedral shape. And that's what the examiner is looking for. They're literally just asking you to say how many bond pairs, lone pairs it's got. Because when I saw these sort of questions without the mark schemes, I always scratch my head and think, what is it you need to say? And I can't recommend enough that you do look at mark schemes and you learn what the examiners are looking for. This is another one now, and you can see here there's a slight complication in drawing our molecule and talking about the shape of that molecule. So the first thing is they asked us to draw a dot and cross diagram to show the electron arrangement in this substance called silane, which is Si2H6. Okay, how are we going to do that? All right, well, let's think about what silane might look like. Well, we know silicon is in group 4, or if you don't, you can find it on your periodic table. So you know it's going to form 4 bonds. And if you look at the molecule there, it's Si2. So obviously you're going to have 1 bond to silicon. And then because you've got 6 hydrogens, each of those is going to have, each silicon is going to have 3 hydrogens attached to it. So basically all 4 electrons on the silicon are going to be involved in bonding. 1 electron to another silicon, and then 3 electrons to hydrogen atoms. So that's your dot and cross diagram, which is great. Okay, hopefully you can draw that anywhere, and I didn't need to do that for you. All right, now we're going to work out the bond angle. And this is where people get a little bit kind of concerned, because, you know, where's your central atom? Well, it's pretty obvious, our central atom. We don't need to worry about all what's going on over here. We're not interested in that. We're just going to pick on this central atom here, the silicon. And we're going to look at our electron pairs. Okay, so we come to our silicon, 1, 2, 3, 4 electron pairs, hopefully, and no bond pairs. Oh, sorry, lone pairs. No lone pairs, 4 bond pairs. So hopefully you know that shape's going to be based on tetrahedral. And that's your answer. Okay, so your bond angle, they've said 109 to 110. Personally, I'd quote 109.5. I'm sure I've done that. And the reason, very simple. There's repulsion of 4 electron pairs, and that gives you that shape. You don't need to say anything else. So I think, you know, being aware of what examiners are looking for is crucial. If we were to draw that molecule, okay, you can see the shape there, and you can see the tetrahedral shape. There's your tetrahedral shape, the silicon sitting on that top position. Okay, and likewise on that way. So yeah, definitely looking mark schemes. Okay, so that's the end of the VSCPR section. What I've done as well is here I've kind of put some slides together that talk about how to approach calculations. And yeah, some of those slides have just I've tagged these on at the end, so I thought I might have extra time. So what I'm going to do is I'm going to go through how to do this calculation, and you know, I think that's one of the things that pupils struggle with the most at A level. And you know, there are techniques to do these calculations, and the first thing we need to do really when we're doing any moles calculation is answer this first question here, and this is key to doing a moles calculation. It's what are you able to find the moles of? You've got to be able to find the moles of something. Perhaps they've given you a concentration and volume. Perhaps they've given you, I don't know, a molar gas volume. They've given you a volume. They're gonna give you something that you can use. And if we look at this question, can you identify what it is we can work out the moles of? Well, hopefully, I'm just going to have a little pause there. Hopefully you can see it's the aluminium. What is it about the aluminium that allows us to work out its moles? Well, we have its mass and we know its AR value from the periodic table. So I've worked out my moles of aluminium, and just to show you how I did that, you know, obviously that formula triangle has to be ingrained. All right, so I've taken my mass divided by the AR in this case, not MR. All right, so once you know the moles of something, and like I say, all calculations are going to involve what can I find the moles of. Once you've got the moles of that thing, you then need to say, well, what do I need to know the moles of? So you can see here we've been asked to work out the volume of hydrogen, and that's intrinsically linked to how many moles of hydrogen there are. So I want to know how many moles of hydrogen there are. So how do I do that? Well, obviously I can link the moles of hydrogen that I've got to the moles of aluminium by looking at your bounced equation. All right, so there's my bounced equation. This is what we call stoichiometry. So what I get my students to do now when I'm doing a moles calculation is I do what I call known to unknown, and I always do it in this order: whatever you know on the left and whatever you want to know on the right. So you've got this kind of ratio between the two, and you can see here I know that I've got 4.85 times 10 to the minus 3 moles of aluminium. I want to know how many moles of hydrogen I've got. So I know how many moles of hydrogen I've got, I can then move on in my calculation. So to do that, the stoichiometry tells me that the moles of the hydrogen is divided by 2 times by 3. And the reason I've done that is I've got 2 in front of the AL, so I'm going to divide by 2, and that's then going to produce 3 moles of hydrogen. Okay, and when I do that, I get this value here. Now I know how many moles of hydrogen. And then the final step in our calculation is, now we know how many moles of hydrogen, we can go up, okay, what do they want us to do with that value? So just going back, you know, as I say, when you do this calculation, you know, you need to look at, well, what can you find the moles of? There's only going to be usually one thing, and that's the aluminium. And then you can relate that to the moles of what you want to know, which is the hydrogen, because we're being our specs volume. Okay, so now I know my moles of hydrogen, I want the volume. Okay, you could, you know, as you know, with gases and volumes, you could use this equation. This is the ideal gas equation. Using that equation, we could work out how many the volume of our gas by rearranging it to this: V equals nRT over P. And I've got some really good advice about this equation. Don't do it. Okay, only do it if you have to do it. So why don't we have to use that equation today? Well, hopefully you can see that something really sticks out here to me, and hopefully it sticks out to you as well. And it's the conditions that they're asking to work out the volume of gas. Can you see that they're at 25 degrees C and 1 atmosphere? Right, that makes our life so much easier, because if you look at your booklet, you should recognise that this is what we call RTP, okay, room temperature and pressure, and we have a molar gas volume quoted on our data book, which is telling you that 1 mole occupies 24.5 decimeters cubed in those conditions. 298 K, by the way, obviously is 25 degrees C. So because this is done at, you know, a molar gas volume that we've got quoted, 24.5, we can actually use a much simpler expression, which is this one here. Okay, and you can see here now you've got your moles of gas is the volume that your gas would occupy divided by the molar gas volume, and because this is done at 29 the RTP, we can use 24.5 here. So let's look at that then as a calculation. So our volume of gas is our moles that we've been able to establish from the balanced equation, multiplied by our molar gas volume, and I get this 0.178. And I'm going to ask you, first of all, a couple of things. Is that good enough? Well, hopefully you're going to be shaking your head and saying, well, no, that's not good enough, because you should always put a unit. Okay, so our unit here, because I've used the molar gas volume in deciliters cubed, that's obviously not acceptable, because the question asks us to do this in centimeters cubed. So again, there we go. You see centimeters cubed being highlighted. So if you look in the data book as well, hopefully you don't need this, but hey, you know, it's not a bad thing to have there. You can see that there's this conversion thing where we can go from decimeters cubed to centimeters cubed. So to go from decimeters cubed to centimeters cubed, we simply multiply by 1,000, and that gives us 178 centimeters cubed. Now, what I thought would be interesting was, well, you know, let's look at, got a red square there. Let's look at using the ideal gas equation. Again, you know, I've got to this point where I've worked out the moles of hydrogen because I want the volume of hydrogen. How would it work with this ideal gas, and why don't we use it unless we have to? The reason for that is you can see here, you have to be very, very careful with our units. All right, so this is why I tell my pupils to avoid using it. First thing is, your temperature has to be at 298 K. So to do that, I've added on 273 onto the 25. And then the one that always catches people out is the pressure. So your pressure is actually in what's called pascals. Okay. Now here it does say it's 1 atmosphere. Bear me a second. Okay. So if you want to go to convert, where is it? No, it's not there. If you want to convert, you basically just take your 1 atmosphere and you times it by 1.01 times 10 to the 5. And this converts, you can see it there. I was looking for it, so I haven't highlighted it. So you can see 1 atmosphere equals that. So that's what I've done here in the calculation. So don't forget to put your pressure in atmospheres. So then that gives us this answer. But again, there's a big problem here. Our volume in this equation is in meters cubed. Okay. So to go from meters cubed to centimeters cubed, you have to go through this conversion. So basically, it's 1 meter cubed equals 1,000 decimeters cubed, and then 1 decimeter cubed equals 1,000 centimeters cubed. The very simple thing to do to go from meters cubed to centimeters cubed is times your value by 10 to the 6, and that gives us 178.5. So you can see, don't use ideal gas equation. The only time I'd use ideal gas equation is if I didn't have a molar gas volume. So let's say the temperature is at 24 degrees C. Hey, I'm going to go the ideal gas equation route. Okay, and that's a little idea about doing a calculation. I've got another one here as well. And again, it's a case of, reading the question and going, well, what have I got? What can I do? And the thing that stuck out for me here in this question is that it's saying it's under the same pressure. Now, it could also have said under the same temperature or something like that. But here, I'm going to go to my gas laws that you've been taught. And I can remember, you've got Charles' law and Boyle's law that tell you what happens to a gas when you change like a pressure, but the temperature staying the same, or you're changing the temperature, but you keep the pressure the same. So, very easy to do. Here, because we've kept the pressure the same, it's under the same pressure, I'm just going to use Charles' law. All right, where we say V1 T1 equals V2 T2. So for us, that's our 125 centimeters cubed. There, 125 centimeters cubed at a temperature of 24 degrees C. Don't forget, though, you've got to be in kelvins with these. Okay, the pressure doesn't matter so much, and the volume doesn't matter so much, but the temperature has to be in kelvins. And applying Charles' law, you can see V2 over T2. Well, V2 is what we want. It's our new volume. Our new temperature is at 52 degrees C. So I've added 273 to get into kelvins. I'll do a simple rearrangement, okay, where we get V by itself. So I'll multiply it by the 325, and that brings me out with 137 centimeters cubed. So I can't teach you how to do every calculation, you know, no one can do that. It's all about practice, going over them and looking for the clues. There's always clues there. Can you work out the moles of something? Or, for example, here it's, you know, I'm under the same pressure, or it's under the same temperature, in which case I'll be using Boyle's law. Anyway, that takes us to our 45 minutes and the end of our presentation. So I hope that was helpful to you. And yeah, I'll wish you a good evening. Thank you very much.